All right, welcome to The Explainer. Today, we're diving into what I honestly consider a thrilling mathematical heist. We are going to explore how a tiny, almost completely invisible fraction is quietly causing absolute chaos behind the scenes in decentralized finance. And, more importantly, we'll see how a 400-year-old mathematical cheat code is being resurrected to save the day. So get ready, because we're about to break out of the computational wood chipper.
So 1.001 seems completely harmless, right? I mean, it's just a tiny little multiplier. But in the world of modern decentralized finance, and specifically inside automated market makers, this seemingly insignificant decimal is the source of a massive computational crisis. It literally forces systems to burn incredible amounts of energy, and worse, it exposes liquidity pools to some brutal vulnerabilities.
But here's the crazy part. Why does this tiny number break decentralized finance in the first place? Well, the mystery lies in the very architecture of the machines running these networks. When you try to calculate powers of 1.001 on something like the Ethereum virtual machine, which is a strict integer-only environment, it triggers this massive cascade of heavy, expensive, and ultimately flawed computations. The machine is quite literally fighting itself just to understand a decimal.
So here's our roadmap for this investigation. First, we'll unpack the DeFi 1.0001 crisis, then hit the hardware determinism wall. Go back in time to Jost Berge's progress tables, break down the square root integer hack, and finally, look ahead to the quantascale era.
Okay, let's dive right into this. Part 1. The DeFi 1.001 crisis and the cost of continuous markets.
To really grasp this, we have to look at how legacy automated market makers, or AMMs, actually handled the incredibly messy, continuous flow of human trading on a discrete digital ledger. To pull this off, they rely on something called a tick. Basically, a tick is just a discrete price interval. To map out all potential market prices, these protocols chop that continuous space up into a grid using a logarithmic formula, 1.0001 to the power of I. Now, this beautifully ensures that each increment corresponds to exactly a 1 basis point change. It is brilliant in theory, but in practice, forcing fluid, human markets into these rigid, logarithmically calculated boundaries requires some incredibly heavy on-chain division.
Which brings us to Part 2, the hardware determinism wall, or what I like to call Silicon's battle of wills. Now, what's really interesting about this constraint is the stark contrast between how computers actually handle math. On one side, we have the floating point unit. Think of this as the FPU gambler. It's fast, sure, but it's lossy and probabilistic. It essentially throws darts at the board, approximating decimals and dropping data just to save time. On the flip side, we have the arithmetic logic unit, the ALU surveyor. The surveyor is strict, discrete, and relies on 100% exact deterministic silicon logic. The EVM strictly demands the surveyor, but calculating 1.0001 natively pushes developers to essentially emulate the gambler.
And when you force deterministic hardware to emulate sloppy floating point approximations, you trigger what researchers call the wood chipper effect. The math is literally just guessing the nearest answer. And because it's a guess, the exact path of that data, its actual provenance, is permanently destroyed. It's kind of like a fruit smoothie. You can never unblend it back into the original fruit. In decentralized finance, this compounds into severe gas spikes during high market volatility, and it leaves liquidity pools highly vulnerable to rounding errors and brutal arbitrage exploits like sandwich attacks.
And the metabolic energy cost of keeping up this computational illusion, it is absolutely staggering. Emulating that heavy, lossy, floating point math can consume up to 98% of a processor's energy for these tasks. It creates this massive, bloated informational debt simply because we are quite literally fighting the computer's native architecture instead of working alongside it.
Let's move to Part 3 and see how this builds into a solution. Jost Berge's progress tables, a true historical cheat code. To fix this ultra-modern hardware crisis, we actually need to travel back 4 centuries. Believe it or not, the key to fixing modern DeFi ticks was unlocked way back in the 1620s. A mathematician named Jost Berge published these progress tables that were designed specifically to calculate compound interest using the exact multiplier of 1.001. Fast forward a few centuries to 2019, when new single-sequence integer discoveries were published in the online encyclopedia of integer sequences. And today, brilliant developers are connecting those historical dots, deploying these exact integer recurrences directly into WebAssembly and EVM smart contracts. It's kind of mind-blowing. But to actually use this ancient math, we have to cross what's known as the semiotic bridge. This is essentially how we translate our fuzzy, fluid human desires, like wanting a perfectly continuous trading market, into the cold, unyielding reality of silicon. We formulate the intent, we compile it through perfectly structured text, and then we execute it exclusively via the exact ALU surveyor, bypassing that FPU gambler completely.
All right, part 4, the square root integer hack and how we natively hit that 1.0001.
Crossing that bridge with Burge's math brings us to the ultimate payoff. Recently, developers experimenting in the best tape square root integers repository figured out something incredibly profound. Instead of dragging around complex, gas-heavy double-sequence methods to try and approximate irrational numbers, they introduced a flawless, single linear integer recurrence. It's this massive simplification that allows a Solidity contract to generate highly accurate rational approximations using absolutely nothing but pure integers.
So, here's how this hack actually works on the ground. You just input exact integer parameters, for example, the numbers 1, 1001, and 2. The contract then generates a single sequence of integers. By simply extracting the ratio between one step of the sequence and the step right before it, the math perfectly converges on our target multiplier. We're literally tricking the computer into calculating decimals using only whole numbers.
So, the crucial point is just how wildly effective this actually is. By using just the first couple of integer pairs generated by this sequence, specifically the ratio of 10,202 over 10,1, the system hits a microscopic error rate of just 0.00485%. It natively calculates the exact 1.001 tick required for stablecoin AMM pricing, completely bypassing that floating point wood chipper. It's elegant, and it just works.
And the efficiency gains here, they're truly paradigm shifting. By replacing floating point approximations with this pure integer geometry, we see a 74 times reduction in metabolic energy. The cost of one of these operations drops to an astonishing 0.05 picojoules. I mean, it completely obliterates the gas cost and totally immunizes the liquidity pool against those nasty numerical drift exploits.
There's this quote from the architecture documentation that I think beautifully captures the philosophy of this whole heist. We move from simply guessing or approximating a curve to entirely possessing the state of the manifold. We are no longer settling for sloppy, rounded-off guesses. By resurrecting 17th century number theory, we've liquidated our informational debt and achieved absolute mathematical truth on-chain.
Which leads us nicely into part 5, the quantascale era, and rethinking market increments altogether.
And this brilliantly illustrates what we call the quantascale philosophy. Instead of just seeing ticks as arbitrary, blocky ladders that we force onto a market, we can now view the market through this space-time scale trifecta. Ticks become emergent recurrence grains, the natural Brownian fabric of market space, captured flawlessly by integer sequences. This allows protocols to dynamically tune tick granularity based on token volatility, creating structures that are incredibly capital efficient.
We've moved from messy, vulnerable guesses to absolute digital certainty, literally bridging centuries of human thought to optimize the very bedrock of our networks. So I want to leave you with this final provocative thought to chew on. Now that we actually have the math to entirely possess the exact, unquestionable state of a system without breaking the machine, what magnificent, perfectly verified system will you choose to build today? Keep orchestrating out there, and thank you so much for joining me for this explainer.